Welcome to Intermolecular Forces. In this lesson, we're going to look at how the polarity of a molecule affects its interactions with other molecules. In your last class with me, we looked at a demonstration where I put pennies into a cup of water. Let's recap that demonstration. You're going to see this cup of water. It's filled to the top, brimming full. I'm going to slowly add pennies to it. Now I've sped up this video so we can see it happen faster. But you can see me adding pennies to it. So as we see pennies being added to the cup, the water level rises, and eventually the water level starts ballooning over the top of the cup. And at the end here, when it's completely full and it starts spilling over, you'll see that it's still ballooned up over the top. We see the water level is actually higher than the rim of the cup. So why is this happening? Well, the reason why it's happening is due to something called intermolecular forces. Let's talk about these for a little bit because they're going to be the focus of our lesson. So intermolecular forces, let's break this down. This root in the front here, inter means between. And molecular refers to molecules. So these are forces between molecules. Specifically, these are forces of attraction. Forces of attraction between molecules. So for the rest of the video, we're going to be talking about these intermolecular forces and what causes them. Before we move into an explanation and looking at what they are, you should also know that they're sometimes called van der Waals forces, based on the scientists that discovered them, van der Waals. Alright, so let's look at the intermolecular forces that occur between polar molecules first. And then we'll look at intermolecular forces between nonpolar molecules. So let's look at a hypothetical polar molecule. We have two atoms, we'll call it A and B, and A and B are bonded together. Let's say A has a partial positive charge and B has a partial negative. So this is our polar molecule. It has a positive end and a negative end. And let's represent this molecule with this image here. So this one will be my A molecule, this one will be my B molecule. Sort of just fill them in to make them look a little bit nicer here. Now let's say this is just one molecule in a collection of many molecules, such as these. So here we have a collection of molecules. We know that the A atom in each molecule has a partial positive charge, so the negative end of one molecule will be attracted to the positive end of another molecule. That positive end will be attracted to a negative end that's nearby, and we're going to see sort of a network emerge between opposite charged ends of the molecules. These attractions are the intermolecular forces, and they occur because the positive end of one molecule is attracted to the negative end of another molecule. We call this a dipole-dipole interaction. That's the name of the intermolecular attraction, dipole-dipole. Because a dipole of one molecule is attracted to the opposite dipole in another molecule. Now because polar molecules only have a partial positive and a partial negative charge, the attraction between them is significantly weaker than the attraction we see between ions in an ionic crystal. Let's take a look at a special case of dipole-dipole interaction. And that special case arises when hydrogen is the positive dipole in the polar molecule. An example of this can be seen with water. And this is going to explain why we saw that ballooning in the demonstration I did before, where the water rose above the surface of the container. Let's look at a molecule of water and then see how it relates to other molecules of water. Here's our model of a water molecule, and here is a collection of a number of water molecules. So what's going to happen with these water molecules? Well, hydrogen we said is a special case here when it's the positive dipole. So this hydrogen's partial positive, so is this one, and the oxygen therefore is partial negative. So hydrogen, when it gives its electrons to a shared pair bond, it's a pure proton left over because hydrogen is only one proton, one electron. So when it gives away that electron to the bond, it's just a proton that's left over, which is a significant source of positive charge. So this is about just as partial of a positive charge you can get without being a full positive charge. So let's show where these attractions are going to take place for this molecule. We're going to have attractions between the hydrogen of one atom and the oxygen of another, like this. Here's another branch, and then we're going to have a connection that way. We're going to see a network going like this and there. Now this case of dipole-dipole interaction, when hydrogen is a positive dipole, is called hydrogen bonding. And hydrogen bonding is significantly stronger than regular dipole-dipole interactions because the degree of polarity with hydrogen being the positive dipole is a lot higher. So hydrogen bonding is our strongest form of intermolecular forces. Now it's important to note that even though we call it hydrogen bonding, this is not a true bond. It's just a way of talking about a very strong intermolecular force. So these are the two cases of intermolecular forces that can come up with polar molecules. Next, we're going to take a look at intermolecular forces that arise from nonpolar molecules. So to understand where the intermolecular forces come from for nonpolar molecules, let's consider H2, hydrogen gas. We have hydrogen bonded to another hydrogen. They're sharing electrons between them, and they're sharing them evenly. That's why this is a nonpolar molecule. But we have to consider that the electrons are not exactly located in this one spot. There's a region of space where we can find the electrons, around or between the hydrogen nuclei. It is therefore possible that at any given moment in time, the two electrons that are being shared between the hydrogens are closer to one hydrogen than the other. Let's say, for example, at a moment in time, we have one electron over here and the other electron over here. They're significantly closer to the hydrogen on the right. That's going to give this hydrogen a partial negative charge, and it's going to give the hydrogen on the left a partial positive. Now, these partial negative and partial positive dipoles are only temporary. They will go away as soon as the electrons move to a new position. But for this moment in time where there is a dipole present, we have a temporary dipole. But how does this matter for an entire collection of hydrogen molecules? Well, imagine for a second there's another hydrogen molecule right next door to this. The partial negative charge from this end of this hydrogen molecule is going to actually make this hydrogen positive because it's closer to it, and that will force the next hydrogen in the molecule to be negative. And so this other molecule has an induced dipole. Again, another temporary dipole created, so you can imagine this happening to multiple molecules that were nearby. As soon as one molecule gains a temporary dipole, it's able to induce a dipole in surrounding molecules. And just for that moment in time where they have this temporary or induced dipole, they will have a force of attraction between them. This type of intermolecular attraction or intermolecular force that occurs between nonpolar molecules is called London dispersion force. And these are extremely weak. These are very weak. They are actually 10 times weaker than your average dipole-dipole interaction. London dispersion forces are present in polar and nonpolar molecules, all of them. However, they are the only intermolecular force of attraction that is present in samples of nonpolar molecules. That wraps up our discussion on intermolecular forces. Write down any questions you have in your notes and bring them in with you to